All right, get ready for a good one. Today, we're diving into a puzzle that feels like it completely breaks reality. We're going to find out how, in the wild world of physics, adding an extra barrier can somehow let more light shine through. I know, it sounds impossible. Let's get into it. Okay, so first let's start with something that makes total sense. You take some regular, unpolarized light and you shoot it through a horizontal filter. Easy enough. All that's left are light waves vibrating side to side. Now, right after that, you stick a second filter, but this one's vertical. What happens? Exactly what you'd expect. Nothing. Complete darkness. The horizontal light can't squeeze through a vertical slot. So far, so good, right? But this is where it gets weird. What if we take that exact setup, the two filters blocking all the light, and we slide a third one right in the middle of them? I mean, your gut reaction has to be, well, that's just another obstacle. It's going to be even darker. How could it possibly be anything else?
And yet, the universe just loves to surprise us. The moment you slide that third filter in, the impossible happens. Light comes back, out of nowhere. By adding another barrier to a system that was pitch black, we've somehow opened a path. This, my friends, is the three-filter paradox, and it is just one of the coolest things you'll ever see in optics.
So, that brings us right to the main event. How on earth does adding an obstacle create a path for light? Well, believe it or not, the answer isn't some crazy complex theory. It all comes down to one single elegant rule. And that one rule is absolutely everything. See, the whole paradox unlocks once you understand what a polarizing filter really does. It doesn't just act like a gatekeeper saying yes or no. It actually changes the light that passes through it. And this rule has a name, Malus's law. Now, don't let the formula spook you. The idea is way simpler than it looks. A filter basically asks the incoming light, hey, how much of your vibe is aligned with my vibe? The amount of light that gets through depends on the angle between the light's polarization and the filter's own angle. It's kind of like pushing a long stick through a fence. If the stick is aligned with the gaps, it slides right through. If it's sideways, it's blocked. So let's look at what this means in practice. If the filter and the light are perfectly lined up, that's a 0-degree angle, 100% of the light gets through. If they're at 90 degrees, like our first setup, 0% gets through. But here is the absolute key to this whole thing. If the angle is halfway, at 45 degrees, exactly half the light makes it. Remember that number, 45 degrees. It's the hero of this story. All right, we have our secret weapon, Malus's law. Now we can finally solve this thing. Let's just follow the light on its crazy journey, one filter at a time, and watch the paradox completely dissolve. Okay, stage one. Super simple. Our first horizontal filter takes all that messy, unpolarized light and cleans it up, letting only the horizontal waves through. In the process, it cuts the original intensity right in half. So if we started with an intensity of I0, we now have I0 divided by 2. Now for stage 2, this is where the magic really starts. That horizontally polarized light now hits our middle filter, the one we just added, which is tilted at some angle. Let's call it theta. Malus's law kicks in. We take our incoming intensity, that's I0 over 2, and we multiply it by the cosine squared of that angle. The big takeaway here is that this filter is doing two things. It's reducing the intensity, and it's rotating the polarization of the light itself. And finally, stage 3. The light that just got rotated to angle theta now hits our last vertical filter. So what's the angle between this light and the vertical filter? Well, it's just 90 degrees minus theta. And here's a fun little trick identity for you. The cosine of 90 minus theta is just the sine of theta. So when we apply Malus's law one last time, we get this final expression for our light's intensity. And after all that, with a little more math magic, we can boil the entire process down to this one beautiful equation. This formula tells us exactly how much light gets through the whole three-filter gauntlet. And notice something amazing. It only depends on one thing, theta, the angle of that middle filter. This is the key that's going to crack the whole case. So we have the equation, but what we really want to know is, what's the best angle? What's the one angle for that middle filter that lets the absolute maximum amount of light through? To find that perfect, optimal answer, we need to bring out the big guns. We need calculus. This is the question, isn't it? We have a function that describes the light transmission. We want to find the very peak of that function. At what angle, theta, do we get the brightest possible result?
Now, we could just try a few angles and see what happens. At 15 degrees, we get a little bit of light. At 75, we get the same amount. But look at that spike right in the middle. At 45 degrees, we get a whopping 12.5% of the original intensity. So it really looks like 45 is our winner. But in science, looks like just doesn't cut it. We need proof.
And how do we get that proof? With the derivative. Now, if you're rusty on your calculus, don't worry. Just think of the derivative as a peak-finding machine. It tells you the slope of a curve at any point. And what's the slope at the very tip-top of a hill? It's flat, right? The slope is 0. So the game plan is simple. We take our transmission formula, we use calculus to find its derivative, and then we set that derivative equal to 0. That's how we find all the spots where the curve is flat, its peaks. And when you do the math, it all simplifies down to this incredibly simple equation. The cosine of 2 times our angle has to be 0. So what angle makes this equation true? Well, the cosine of 90 degrees is 0. So if 2 times theta equals 90, then theta has to be 45 degrees. And there it is. That's the confirmation. Calculus gives us the definitive, undeniable proof. 45 degrees isn't just a lucky guess. It is the one, single, unique angle that unlocks the maximum possible light. The paradox isn't just solved, it's optimized. But this whole thing is so much more than just a cool trick with sunglasses. Solving this paradox actually uncovers a deep, profound principle about how the world works, about how things that seem totally incompatible can actually connect. This quote really nails it. The horizontal and vertical filters are orthogonal. They're fundamentally opposed, with nothing in common. That 45-degree filter, though, it acts as a perfect translator. It speaks a little bit of the horizontal language and a little bit of the vertical language, creating a bridge where there was only a wall before. And this isn't just about light. This pattern is everywhere. In quantum mechanics, a superposition state connects the incompatible spin up and spin down. In math, a 45-degree rotation is what connects the x-axis to the y-axis. In communication, a translator connects two people who speak different languages. It's the same fundamental idea, playing out over and over again. And that kind of leaves us with a final, bigger question. This simple experiment has given us a blueprint for building bridges. You take two opposites, and you find a mediator that shares a piece of both. So where else could we use this idea? In technology, in our communities, in our own lives? Where could we find that magic 45-degree angle to connect two things that seem impossibly far apart?